Hello and welcome to another episode of the Oxford Online Maths Club. It's just me on the stream today, but that's because this is something of a bonus episode. We're at the end of season 7, don't worry, season 8 is just around the corner. We're doing a two-week break for Easter, but this is a sort of bonus episode with just me. And also some of you who I can see in the Slido chat. Look at that segue, isn't that professional? I can see some of you over there. Hi to Herb and an anonymous person and me. If you want to join in with Slido, you can do that over at slido.com/OOMC. That's how you can let us know where you're watching from or ask us about A-levels. Ask about A-star and A-level maths. They say that's not possible. I'm trying to find out what qualification they're doing where there aren't any A-stars. Because there's lots of qualifications when there aren't any A-stars. Hi to some. Oh, right, okay, here we go. This is how I know that I've turned my microphone on, because people have responded to my call to action with the word hi in chat. Hi, anonymous person. There you go. Hi, neutrino. Ah, okay, there we go. Good. Something's working. I think I've got Callie in chat again. Yes, I do. Hello, Callie. Right, good. Oh, and hello, anonymous person as well. Who might or might not be Callie. Right, okay. Very loud construction noises. We're going to try and ignore that. So, my plan today is to try and get to hyperbolic space. So I've got two routes that we might take to hyperbolic space. I'm going to do a vote. So in a minute we're going to do I think it's a bit of a gimmick, but I'm going to try doing a vote for what route we should take. But first let's do the one we normally do, which is how's your day today? I think I'm having something of a 4-star day, he says, over a loud banging noise that's coming from... I'm sure they make it extra clangy, just as I say hello and welcome back to another episode. They go, right, that's our cue, time to drop everything. Oh, there's a 3-star day for chat. Yes, so question in chat, what is hyperbolic space? Exactly, I'm hoping we'll get there. We're going to try and get there, and along the way, find out what on earth that is. Callie in chat says hello. This is only not to be anonymous. This makes me think. There you go. G'day. Right, okay. Chat's not having a great day. That's a shame. I hope that the following hour of mathematical nonsense is a good way to get that score up. Oh, it's a weird distribution though. It's like trend, 5 stars, and then more 4 stars, and then more 3 stars, and then maybe some sort of survivorship bias, right? Because continuing that trend, there will be even more 2 stars and 1 stars, but none of them are here. Oh, they're asking about Singaporean A-level maths. Right, I thought it'd be something like this. So Singaporean A-level maths is different, right? Singaporean A-levels? Quick pause while I look up Singapore A-levels. Yeah, that's different, isn't it? Yeah. There's a Singapore requirement on the international qualifications page, which I think I linked you to. Okay. Good, right. H3 maths, we don't ask for H3 Singapore maths. You can do it if you like, but we're not really sure how often people are even able to do it. I think it looks fun, so if you've got the chance, go for it. Hello, hey, you're late, you have not missed anything. You've missed me doing some chat wrangling, by which I mean trying to work out how to use chat. Right, okay, that was the poll, that was the hood. How's your day, poll? We're doing great. Hi, hey, you've come at just the right moment. Hyperbolics. Right, I've got a big plan for this. In fact, I've got 2 plans. There are 2 ways that I can show you what hyperbolic geometry is like. One of them is a bit more, for want of a better phrase, one of them is a bit more pure maths, in that I've got a whole big pile of heptagons. Heptagons? Some people call them septagons. Sevengons. I've got some shapes. I'm calling that roughly pure maths. And I've got another one that's a bit more like applied maths, which is a different route that we could take, where I've got a traffic puzzle. It's kind of travelling salesperson ish, but not really. It's not the travelling salesperson problem, don't worry. Famously hard problem. No, I've got a different one. And I think we've got time to do both, but I thought I'd let you vote on which one we do first. This is a bit experimental in a way. I don't often shuffle my content around based on a chat vote. Let's find out. So one's called the fast lane because it's a traffic puzzle to do with taking the slow lane or the fast lane. And the pure maths one I've made sound purposefully unappealing because I think it's got an advantage. I think from previous times we've asked about this, chat have been more interested in pure maths, and in fact heptagons is winning, perhaps because I've called the other one something practical and good. Was the traffic puzzle ever going to win? Truth is, it was rigged from the start. Let's give that a moment to let the fast lane catch up a tiny bit. Ironically. And again, I've got no idea how long I'm doing on this, so we're going to see how this goes. Cool. Okay. Always good to see chat interaction. You've told me how your day is. You've told me that you like heptagons. Let's go over there. Okay. I think heptagons have won it. Fast laners, don't worry. You will get your time. You will get your time. Okay. So I'm going to show you some heptagons. But first, I want to show you other polygons. For this, I need to switch to reality, which I think I have. Yes. Play animation. Ooh. Okay. Oh, that worked really well. Okay. Have I done this before this year? I'm not sure if I have. Reality. Also reality. Right. Matches right. Left matches left. It's got the topology of a cylinder. Anyway, I've got some pentagons here, not the advertised heptagons. Sorry. I want to talk about tessellation a little bit. You probably know that when you're tiling, you could use triangles, you could use squares, you could use hexagons. There's kind of a missing one there. Nobody tiles with pentagons. I guess that's because the angles don't work out, right? So if you live in 2D, this is kind of the end of the story for how your tiling with regular pentagons might go. There are some irregular pentagon tilings that you could do, but if your job is to tile with pentagons, then it's a bit stark. But something we could do is try forcing it to work and see what happens. So let's take these 3 pentagons, which don't fit together, and let's try sticking them together. I've brought some rather fetching space-themed sticky tape for this, since we're talking about spaces. Okay, so, this is just like Blue Peter. I'm going to stick that one there, and then my plan is to stick these 2 together as well, like this. Glue those 2 pentagons together, and then, tricky one, I want to glue these 2 pentagons together. So I want to do something like, I'll pick it up I think, to get these 2 to join together, I need to do some bending. And you'll notice that I have cheated by bringing the pentagons up into 3-dimensional space, which is where you and I live, to give me this shape, or a little hat-shaped thing, which you've maybe seen before if you've studied platonic solids, which in 3D are shaped a bit like regular polygons, but solids where you put together regular polygons as the faces, you try and make all the corners the same, you can make these things called regular polygons. There's one called a dodecahedron that's made of pentagons like this. But I suppose the gimmick there is that you can't put pentagons together on the flat plane, but you can put them together in 3D. There's a kind of almost curvature effect there, where this thing, instead of lying flat, curves around. I know each pentagon is actually quite a flat surface, but if we imagine that it sort of smooths out, maybe you get some sort of curved shape. Right, let's stick some more on just to see what happens. Okay. When we originally pitched this show, Oxford Online Maths Club, the way we described it to people was, like Blue Peter, it's a magazine show where they do lots of different things. We want to do that, but for maths. So I want to piece this together over here. It hasn't quite worked out like that, but sometimes I get the sticky tape out and I think, yeah, This could be Blue Peter. For people watching outside the UK, you can Google Blue Peter. It's a kids TV program where they learn stuff and also make stuff. It's been running for an extremely long time. This is all cover for me doing an incredibly slow job of sticking together some pentagons. Where did I start? I think I started on that one. So I'm going to go outwards like this. And key skills in doing this, if you want to try this at home, lining things up and keeping track of what's supposed to glue onto what. Okay, let's put this one on here. I think I'm going to turn it inside out to line that up. And let's put one more in there. I can kind of see where I want this one. How am I going to do this? I think I'll buck the pattern and work. I was sort of working outwards from a point over here, so I think I'll put it over this side. The good thing about using thick, opaque sticky tape is that you can't tell whether I did that edge well or not. It's all hidden underneath the tape. Okay, and let's piece that last one together. Now you can tell that I did it poorly because it's not going to match. Okay, good. Okay, so I put another round of pentagons on, and I've got something that is even more curved round than it was before, like a sort of football, but starry. Let's show it on the other camera as well. I'll show you this kind of shape. From slightly further away you can see the curvature a bit better. Okay, so the point of doing that was to show you that, okay, you can't put pentagons together in the plane, on the flat surface, but if you try and do it anyway, then you can discover this kind of curved surface, which you've maybe seen before. That's going to curve around just like a sphere would, like a football, or like a dodecahedron. Okay, nothing new there. I should really, for pattern reasons, I should do hexagons next. We've got pentagons, so really I should now spend about 5 or 10 minutes sticking together hexagons to make a flat grid, and then we'll all look at it and we'll say, yeah, that's what hexagons do. We're going to skip that 10 minutes and go up to heptagons instead. What are we calling them? Are we calling them heptagons or septagons? Feels like a poll for chat, doesn't it? Let's find out whether chat's more. One of them I believe to be a mix of Greek and Latin. Let's go heptagon and septagon. Feels like, oh, which should I say? There's one vote there. Okay, save and launch. Yeah, there we go. I built it. I built it. That can cover time as well. Okay, here are some septagons. Now these are regular septagons. Blue Peter phrases. Here's some I made earlier. So these also don't tile the plane. This time because the angles are too large. I suppose if you think about it, the angles in a shape, if we were going to have 3 of them at a point, we'd want them to be hexagons. And if we were going to have more than 3, we'd use squares or something. Fewer than 3 doesn't even really make sense. So septagons and upwards is sort of hopeless for tiling the plane. But maybe we could try doing the same thing again to just force it to work and see what we get instead. Okay, that's my plan for the next 5 minutes of sticking things together. Chat's voted that I should say heptagon, so heptagon I shall say. Okay. Right, okay. So same idea, I'm going to glue together my heptagons. That was a good start, I think. Let's get the next one in there. And then I want a bit of tape there. If you'd like to play along at home, when I do the further reading for this episode, I'm going to give you a download file to, if you'd like to print out some heptagons yourself. I suppose semi-interesting challenge to work out how to make some heptagons. Right, here's the tricky bit. I think I've got to get that over there so that I can make enough space for, you see these ones, I've got to go out like that so that I can put the tape in. Okay. Oh, this is really fiddly. Let's see if we can make it work. There we go. So from below, maybe it's clearer what's going on. Let's display that one outwards. Okay. So this shape's already quite unhappy with me. I think Okay, so not at all clear where this is going. This does not remind me of any of the platonic solids. And quick bit of remembering about platonic solids, yeah, none of them have got heptagons on them for these 3D shapes. And also it seems unhappy in a way that it's got curvature to it, but not in a nice consistent way like the pentagons, which give this nice everything curved around neatly. This is trying to curve in a way in two different directions at the same time. Let's put 3 more heptagons on. Maybe I should switch between them, but an 84:16 ratio, is that the poll result? That sounds extraordinarily challenging. If you've been watching much of Season 7, then you'll know that these sort of challenges are very difficult for me. Right, okay. Annoyingly, I've only brought 6 of them with me, so rather than 7, which would be an excellent number of heptagons to have. Septagons to sav? No, you've only got to flip the H's and S's on the word that means the 7 gone. Okay. Well, it's a strange episode, isn't it? It's James on his own, trying to keep up with chat, shall I say. Yeah, so the plan is that this is going to create a space unlike a football, unlike a dodecahedron, unlike a sphere, a space with negative curvature, and it's a model of hyperbolic space. We're getting there. There we go. Okay, now it's getting really angry. Good. So as I put that one on, maybe you can see from the way it rocks backwards and forwards, it's now much less happy with me. If you're printing this at home, I advise you to print it on quite bendy paper. Okay, let's stick a couple more on. The thing that we should see as we stick more of these on is that the wobbly bits get more and more wobbly as we go. In a way, this space doesn't really work inside R3. I mean, that's a weird thing to say while I'm physically building it in R3, but you know. Okay, and then one more, which I think I've got to put right there. So that's a challenge. It's slightly weird to work with this. This bit looks really, the paper here is really tightly curved, but you can kind of massage it around to convince it that maybe the problem should be over there instead. That locally, each point that I'm making is the same as each other. Just like the rule for a dodecahedron, all the corners look the same. Locally, each corner is the same as each other, so my job shouldn't really be getting harder. I guess there's a consequence of having lots of other heptagons hanging around. Ooh, that one was pretty bad. Let's redo that one. I also recommend using some sort of masking tape or something that you can replace, because if you want to have another go at it, being able to change your mind a little bit is good. Okay, so now we've got something that I would describe as really quite unhappy. Maybe it'd be happy if it went the other way. No, that's made it much less happy. Haha, good. Okay, so maybe you can see it's a little bit hard onto this camera, but the kind of outer circle, adding that in has created a shape that's even more twisty around the outside. I'm going to try and show you a side angle. I'll give it a go in here. I'll give it a go on this camera as well. So I've got this thing that's shaped like this. And I think I'll leave it as homework to try and do this with another round around the edge as well. I should say I've seen crochet instructions for this as well. I don't crochet, so I haven't done the crochet version on stream. But I've seen versions of this where you crochet. I think when people do crochet, there's a way you can make, I don't know, beanie hats or something. So there's a way to make something a bit like the pentagon shape, where as you crochet ring after ring after ring, you adjust the length of those rings so that I guess you get to the wider bit of the hat and it's wider. if you change the rule for how you change the size of those rings as you go round and round, if you change the rule, you can generate something more like this, which expands outwards. So I want to make a point, which is, if you take this version, maybe I should be clear that I'm not claiming that what I'm holding now, it's a rather sad collection of stressed paper. I'm not claiming this is hyperbolic space. I'm claiming that from some angles, this has got properties in common with hyperbolic space. For example, if I kind of flatten it out a bit so that the middle is relatively normal, try and move the stress to the outside, maybe I'll curve that bit around, curve that bit around, curve that bit around. Then from above, you get this situation where near here, as you're looking straight down on it, moving around here is relatively easy, but moving around a circle around here is really difficult because you've got to go up and down over all these wiggles. Now, the way I've set up the camera, you can't quite see the wiggles, and that's good for the point I'm making. That to walk round a large circle, far from the middle where I started, to walk around a large circle, that's actually quite a lot of distance because of all the wrinkles. In some sense, there's sort of exponentially much wiggling going on. So what we could draw is a map looking down of this space where, as you go further away, these heptagons, as they get more wrinkled up, as they get smaller, they should appear smaller to a viewer looking down from above. And that's the reason that this is a sort of non-Euclidean interesting geometry. Because when you draw a map of it, you can see the effect that distances aren't the same as they would be in our normal Euclidean world, kind of because of all the wiggles. Yeah, it's just a bit like contour lines on a map. It sort of gets worse and worse. I'm surprised how well this one's behaving. I made one at home earlier, and it was much angrier with me. Maybe I just taped it differently. Okay, I want to switch to show you a map of hyperbolic space, and let's do a little comparison. So here's a map of hyperbolic space that I got off Wikipedia, and it's been tiled with heptagons. I think each of these heptagons is supposed to be the same size, but the ones around the edge, they look smaller to our Euclidean eyes, but they're the same size because distance itself around the edge is longer between 2 points. So that 2 points here, this distance and this distance, in our Euclidean sense, the small line is smaller than the big line. But for a voyager in hyperbolic space, where you might have to travel over lots of wiggles, it might be the same. Okay, so that's a glimpse of hyperbolic space. The way you make it really is sort of the opposite of the way that you make a sphere, and it comes with lots of challenges to do with map projections. Maybe you know that when you look at a map, depending on what sort of map it is and when it was made, it's maybe got Greenland being weirdly big, and when you look at that and you see Greenland being enormous, you're supposed to think, aha, Greenland is not actually massive, that's just a feature of my map. And this is kind of similar, right? That these ones in the middle are not actually massive, it's a feature of this map. This circle is not itself hyperbolic space unless you change what you mean by distance. Okay, there's all sorts of fun stuff going on in hyperbolic space. To do with this notion of distance being different, to define this different measure of distance, which in my head at the moment is because it's negative curvature gives you lots of wrinkles that you have to navigate, which is not a formal definition. Okay, I want to show you one more picture because hyperbolic geometry inspired artists like MC Escher. So MC Escher, famous for drawing those kind of impossible triangles, and the one with the staircases that go in all different directions, and the waterfall that feeds back down behind the other bit, and then it goes back round again. Those kind of optical illusion woodcut pictures. MC Escher had a field day with this. MC Escher really liked it. Here's one picture that MC Escher drew. So this is not heptagon tiling. This is a different sort of tiling. And because it's MC Escher, it's also lots of fish. And I really like the way this uses different colours to emphasise different parts of the tiling. The image I've stolen there and put on screen is not extremely high quality, so you can't quite see the way it breaks down at the edge. It repeats into these smaller and smaller copies, well, smaller and smaller from my Euclidean geometry point of view, round the edges. From a hyperbolic point of view, it's just tiles. They're just all the same size. So MC Escher is really inspired by this kind of mathematics. It's an example of something called non-Euclidean geometry. I realise I said Euclidean geometry quite a lot there. So Euclidean geometry is the sort that you learn at school, where you know the distance between 2 points is given by Pythagoras' theorem in terms of the coordinates. If you start messing with that, then you can get all sorts of fun. If you like, you're just distorting the picture. You're doing these things where different bits that kind of clearly should be the same distance, a centimetre near the middle of the circle, a centimetre near the end of the circle, things that maybe clearly should have the same distance actually have different distances. But if you like, this is a map of a different space, a map of somewhere that we don't live. Good. Okay. Really links into a lot of modern theoretical physics, by the way. I'm trying to segue into the applied maths bit. Fast lane people, this is coming. Yeah, XKCD's done things about maps. Does the shape look smaller the further away from the centre of the circle in the same way that things look... right, things look further away in real life. That is a good point. We had an episode a couple of months ago, didn't we, on projective geometry, which was all about allowing for sort of perspective and looking at things very far away. There's similar ideas there. In a way, if you build a map of the projective space, then you might find that it's got some similar properties. I think it's not quite the same scaling that you get at the horizon, but it reminds me of that. Maybe I'm wrong, maybe it is all the same. Homework. Is everything all the same? Right, okay, we're going to get to the rules. I've decided not to start with rules. This is an ambitious attempt to maybe end up with some rules that hyperbolic geometry does or doesn't do. Okay, look at this timing. past, we're going to switch to talking about life in the fast lane. So people who voted for the fast lane, your time is now, as soon as I find it. Where did I put it? Oh, it's over here, it's over here. Oh, I made graphics, look. What happens if I prepare stuff? Look, you get heptagons and you get... Isn't that an amazing car? Okay. This one's inspired by real life. We're sort of starting again because of the vote. This could have been the first thing that we did. So forget everything you know about hyperbolic geometry and distances near the edge being somehow larger than they appear. Forget everything you know. Okay, so here's the kind of applied maths problem. You're driving your car down the motorway, which in the UK we drive on the left and the slow lane is on the left. So if you're watching this in one of the many countries where they drive on the right, then sorry, please reflect your screen or something. Okay, here's the problem. You want to get from A to B A is where you currently are, I guess. So let's put A. And you want to get to B, which is, oh my goodness, all the way over here. Car maybe not to scale. And you have some choices about how you do that. You could stay in the slow lane. I seem to have taken that with me, there we go. You could stay in the slow lane and just drive slowly from A to B. Or you could live a little bit and you could get into the fast lane, get into this medium speed lane maybe, driving the medium speed lane and get to B like that. Or you could really push it and you could go all the way over into this very fast lane, which is then very speedy, but then you're going to have to get back into this lane over here. So you're maybe considering a route that goes from A to B, where you go round like this and then back again, perhaps. Or maybe you're considering a route that looks more like get in the fast lane, go in the fast lane, and then back again. So, if you've got 3 lanes like this, then it's kind of an interesting problem as to where should you drive. I suppose I'm imagining that this bit of changing lane takes you time for 2 reasons. Partly because there's some distance that you have to move, and partly because you're going very slowly. You're in the slow lane. I guess I'm treating the slow lane as a kind of speed limit on how fast you're moving as you move, whether you're moving forwards or moving sideways. And I am an applied mathematician, but I am neglecting road safety, so I'm considering this to be a perfectly acceptable thing to do, to just drive your car sort of, I guess I should rotate this, just drive your car horizontally, quite slowly, into the fast lane and then speed off into the sunset. Please don't please don't arrest me. Yeah, extremely fast around Oxford. So this is a kind of puzzle that you can kind of work out. Essentially you want to do something a bit like, I don't know if people have seen this problem about the dog at the beach. Let's do the dog at the beach problem over here really quickly. You're at the beach, you've got a dog, this is you. You throw something into the water over here, so you've got beach, water, and the dog would like to go and get the thing. Then running on the beach is, no wait, hang on, running on the beach is fast, I think, for dogs. Gosh, I'm talking like I've never seen a dog. And swimming is slow. So for your dog to get from A to B, this is the art stream we know and love. That'll do. Hang on. Little collar. Little tongue. For your dog to get from A to B, it's going to want to do something like quickly run across the beach and then do some slow swimming. So the dog beach problem works like this. The dog runs quickly to the water's edge and then swims slowly to point B. Like that. And you can do some geometry on this. If everything's sort of at right angles and straight edge of the beach and you know some numbers for the problem, then you can do some kind of geometry on this. You can write down some distances, you can write down some speeds, you can do some all of that jazz. The surprising thing that you find out is that your dog... Do people know this problem? Oh no, people are asking me questions about the other one. What if you're in the fast lane and many other cars block your way back to B? Yeah, good question. I think I'm imagining, because my driving is so dangerous, I'm willing to consider things where you drive up to B, turn your car 90 degrees, you just drive slowly into B. Because my driving is so dangerous, I'm suggesting, I think, that we do this when no one else is around. So there's no other cars in the way. That's my one concession for safety. Fast lane, and then I would consider, just sort of driving sideways. I really wish I could rotate this model. Can I rotate this? Oh, I can rotate this. Yes, there we go. Okay, so I'll consider something where you drive and then you do some sort of like sharp turn and charge straight at B. It'll cost you a bit slow because you'll have to drive through some slow lanes. Dog problem, probably been mentioned in Math Club before. I'm always talking about the dog problem. I love the dog problem. If you've just seen it for the first time, I'll save you from doing all the geometry. The surprising result is that your dog behaves exactly like a beam of light. A beam of light being refracted as it changes between the two media. So if you've seen Snell's law, then wow, you've seen a lot of physics. If you've seen Snell's law, then you've seen this rule about how a ray of light gets deflected as it enters a different media where it's got a different wave speed. That's some sort of high-level physics that you can get out of just the geometry of your dog just trying to get there quickly. So, follow-up questions. Does your dog actually do that? And does this mean that your dog is in some sense laser guided? Yeah, okay, I talk about the dog problem too much. I love it though. You can turn as sharply as you like. I will allow any sort of nonsense. Just show me the route and I will show you how to drive. I think with 3 lanes, the solution is going to be something like, it's going to be tricky to do the maths and it depends how fast the route, depends how fast we're going. But it's going to be something like get to the middle lane, get to the fast lane, maybe at a different angle there, get to the very fast lane, and then don't bother going any further into the fast lane, but just go like along the boundary of the fast lane, like really skirting the rules, so that you're like, oh, I'm just in the fast lane, I'm allowed to drive fast. But you haven't wasted any time lining up with the middle of the fast lane. Hog the inside of the fast lane, and then get back to B. And I reckon there might be some symmetry to this. I've drawn it really asymmetrically, but I reckon there might be some symmetry. After all, if I think that the fastest way to get to this point is by doing this, then for the second half of my journey, maybe I should do the fastest way, which should just be a mirror image. The road is kind of mirror image above. So I've drawn this really asymmetric, but I think it should have some mirror symmetry. Would I take into consideration acceleration or braking at the turns? No, and I am going to model the car as a particle for this. So like I was modelling the dog, it's just following a line. I guess I'm modelling this as find me the line to go along. Maybe I change my angle here, maybe I now drive straight for a bit along here. I'm really glad I found this rotate feature, this is great fun. Maybe approach that from an angle. Okay. Yep, so what's the refractive index of the fast lane is a sensible question. Because that influences the angle you want to approach the fast lane from, so that you can do this refraction right into there, just like that. These problems are really awkward though, because even if you know Snell's law as a relationship between the angles, you've still got to do loads of trigonometry. It's really tough. The middle lane matters a bit because I guess its presence and its different sort of medium speed means you don't want to spend too long in there when you could be in the fast lane. But you also don't want to waste time driving to the right, given that you're just going to have to drive to the left again at the end. So there's a really nice version of this problem, which is to go to the continuous version of this problem, which sounds mad. Let me write it out. So what if your speed, and I suppose that's a speed limit, but I always drive at the speed limit. God. What if your speed was proportional to x? So instead of having 3 lanes, infinitely many lanes, whatever your value of x is, that's how fast you're allowed to go. Appropriate proportional factor in there, so that maybe you're so many meters across, and that means your speed limit is now 60 miles per hour or whatever. Yeah, something critical angle. Yeah, there's some real angle stuff going on here, isn't there? What if your speed was proportional to x? So this is a much harder version of the problem. Really quite a lot harder. It's like having in Snell's law, but instead of having several media in slices next to each other, it's like having infinitely many of those, or a smooth gradient in the speed. So a smooth gradient in the material property. So like shining a light beam into water, but the water changes, I don't know, density or whatever with depth, so it really affects the refractive index all the way through. That's a much harder problem, but has a nicer theory. We're going to have a quick look at the theory. So first, quick recap on how distance works. So if you've got this curve y of x for a curve like this, and you want to find the length, then what you need to do is actually a little bit complicated, because at each point here you want to sort of add up lots of little bits of length, and maybe you can see that when the gradient is high you don't move very far to the right, but you get some for each unit of length, but when the gradient is low you get lots of motion to the right as you move one unit along the line. So the formula for length is actually a little bit complicated. You can do it as an integral if you like. So if I kind of zoom in on one of these things, so zoom in on one of these, what's going on over here is I've got some curve like this, and I'm interested in how long this bit of line is in terms of, because I'm going to do some integration or something, I'm imagining just a little change in x, and there's a corresponding change in y over here, but just as a little bit of the curve how much changes in x and y, there's some little change in length here, which is something like Pythagoras time square root dx squared plus dy squared. So the thing you actually integrate is you integrate 1 plus dy by dx squared with respect to x, where I've kind of pulled out a dx from inside the bracket. I'm not really trying to explain why this is true so much as giving you this sort of thing is unfortunately how you work out how long a curve is. Is a step harder than that, yeah, absolutely. Not close. It's taken by people at the end of year 13 rather than the start of year 13. Nowhere near. Also based on loads more different sorts of mathematics. Okay, so I think this is my integral for length, or arc length of a curve, and this is a good way to formalise a problem of what's the shortest distance from A to B. I think you already know what the shortest distance is from A to B, right? Straight line. But if I showed you some other random curve, I said, no, I reckon that's shorter distance, then I guess the way you would disprove that is to do something horrible like integrate this. So what we really want to do in order to prove that the shortest distance from A to B is a straight line will be to do something like minimize this. By which I mean choose the correct y of x. It's a bit tricky, isn't it, to imagine choosing the correct y of x so that, oh my goodness, after you differentiate it, square it, add one square root and integrate, you get a small number at the end. That's horrible. That's really nasty. So it's really not obvious what that's got to do with straight lines. Also, the answer is not supposed to be a straight line. I'm pretty sure the answer is not just drive in a straight line in the slow lane. Feels like we're missing a trick there. At least a little bit of give and take. Maybe I'm wrong. And that's because I haven't allowed for the speed limit. I haven't allowed for the speed yet. So this is a nice formula for the length, but what I actually want is time. What? So although the pink line I've drawn, sure, the pink line that I've drawn is longer, more journey, than if I just did this light blue line from A to B. Sure, the pink line is longer, but I think maybe it might be faster, which means what I want is not quite distance, but time. So I don't quite want the length of that, I want how long it will take me to drive. But luckily there's a nice relationship between, you probably know a nice relationship between speed, time and distance. There's a nice relationship between these three things. Here it's a little bit difficult because our speed changes with x. At different values of x we've got different speed, but that's okay, it just means it's inside the integral. And if you like, when I zoom in, as well as allowing for the length of this bit of line, I should remember, and over there, my speed is something to do with x, so I'll do that bit really quickly. And what I want to do is actually minimize something different. So, okay, I'm going to write down another integral. Sorry to have two integrals after 5 PM, when you're probably on Easter holidays, but I'm going somewhere with this, I promise. Which is this. So, the time that it takes is something like, well, integration or summing or adding together lots of little bits of time that it takes me to do each bit of my journey. That's what integration is. Each bit of my journey along that pink line. And I don't want the distance, I don't want the physical distance, I want the time, which is something like, oh my goodness, distance divided by speed? Is that the right way up? Distance divided by speed? Yeah, I think I want distance divided by speed. Distance divided by speed. So if my speed here, speed proportional to x, and this thing upstairs is distance. I guess the distance of that little bit. Sorry, I keep pointing at this little triangle because everything is kind of integration and made of lots of small bits. How can you prepare for STEP other than past questions? Somebody's asked in chat. I guess you've got to be really good at lots of different sorts of maths. So you might try revising lots of A-level mathematics. The syllabus for STEP is a thing that exists that you can look at. If you are a female mathematician in, well, I guess within travel distance of Cambridge, in year 12, or non-binary, then there's a STEP summer school hosted by our friends at Cambridge, in particular Murray Edwards College. There you go. If Eve's watching, look, I plugged your summer school again. You probably thought I wasn't going to because I didn't do it at the start, but got in a plug for your summer school. Yes, there is a K downstairs, really, I suppose, because we don't know. You're right, I should probably have a K in here. I might put 1 over K outside, because that constant doesn't depend on X. I might bring it out here. And then I might quietly forget about it, because if I can minimize this, if I can choose the value of Y that makes this small, then, okay, everything's multiplied by 1 over K. It'll be a smaller number at the end. Yeah, how on earth do you evaluate that integral, right? Let alone minimize it. How do you evaluate it? If I show you some curve and say, aha, I've decided that you should go straight to the fast lane and do a little curve, screeching handbrake turn, which I'm sadly not modelling. Sorry to the person who asked about screeching handbrake turns. There's a little curve where I've got some derivative, and then straight line upwards. How do you even do this integral? The straight line upwards is actually pretty bad for me, isn't it? Because that's infinite gradient, so let's change the question slightly. Upwards going at a slight angle like this to get into the fast lane. I guess I would have to write down what y is, and then differentiate it, then square it, add 1, and then square root it, and then divide by x to just hope that I can integrate it. Or maybe I'd give it to a computer. Maybe that's a bit cheap, isn't it? But maybe I'd say, okay, look, I've decided that I want to drive like a maniac, by which I mean using sine of x. So this is cos squared and then plus 1, so something to do with cos 2x, and then square root it, so maybe something to do with cos x again, and then divided by x, so good luck. I don't think I can do this integral for any function that I can think of. Right, which makes this next bit even more surprising. That although I don't think I can minimise this, although I don't think I can evaluate it, I can minimise it. Because there's some amazing theory for doing problems like this. Let's draw a box around it. We're bringing out all the technology today. Oomph. Technology. Behold. Hang on. No. There we go. So minimising things like this, there's some maths for that, which became popular maybe 100 years ago, a bit more than 100 years ago now. People like Emmy Noether worked on this. I'm more than 100 years out, aren't I? Because I'm about to tell you they're called the Euler-Lagrange equations. Okay, my history is slightly off. Mastered by Emmy Noether, previously worked on by other mathematicians. Works like this. This is things called the Euler-Lagrange equations. Which are really a bit like the way, you have a rule for how to minimise a quadratic or how to minimise a polynomial or some function or something. Your rule is that at the minimum, I know something about what's going on at the minimum, it should have no derivative, derivative 0 at the minimum. The Euler-Lagrange equations are a kind of souped up version of that. For this sort of problem, where we're minimising something that's an integral over an integrand involving some unknown function y. It's really amazing maths. I don't think I'm overselling it. So there a way to turn this, if you've got something that depends on y and the derivative of y, which I seem to be writing as, I'm going to write it as y prime, sorry. Like this, to minimise this, that turns this into a lovely equation, if you've got one unknown, a lovely equation like this. Which is then a differential equation, and yes, half of those d's are curly d's, partial derivatives. Don't worry about it, I'm just showing you the shape of this thing. To convert this problem into essentially, some derivative is 0. And I know that thing on the left is unfamiliar, doesn't make any sense. Most of the symbols you don't recognise. But I'm telling you, this is a sort of derivative, which you've got the Lagrange equation saying, that's 0. So just like, you might be struggling away with a polynomial, but you might be able to find the turning points or find those critical points by differentiating. The Euler-Lagrange equations give you a way to take something like this and convert them into a differential equation. Hi Zoe. Oh, it is the end, isn't it? I've got 5 minutes. Good. Time flies. Yeah, how do you prove it? Lightning speed explanation of how you might prove something like this. Works like this. Consider y is equal to y naught plus just a little bit, let's use a different value, just a little bit of perturbation. So I've maybe got my perfect y0 plus just a little bit of perturbation. Find out what happens and differentiate respect to that. The idea is that if y0 really is the function that minimises this expression, so up here, if you've really got the correct y, then if you add just a little bit, if you add just a little bit of extra function phi that maybe changes the shape a little bit, then that should have, to first order, no effect. Just the same way that if you start at a turning point here and you move just a little bit away, then there should be zero derivative. Alpha kind of models the extent to the perturbation. Yes, it's just like the Brachistov-Crone problem. It's the same theory, because you can write lots of physics. You can write lots of physics in this format. Minimizing an integral is a good way to write down lots of physics, and it can explain a big variety of things. But let's get back to the fast lane example, because after doing this and then solve, which is a fair bit of maths, it turns out that the answer is beautiful. It's semicircles centered on the line x equals 0. Semicircle centered on x equals 0. I've got a Desmos thing for this. So you've got your 2 points. You want to get from A to B. The fastest way to do that, if your speed is proportional to x, the fastest way to do that is to use a semicircular arc to go into the fast lane a bit, constantly be steering to get back out of the fast lane and get to your point B like that. And if you like, what we've got here is another map of some unusual geometry where distances over on the right are actually shorter than what looked like the same thing on the left. Over here, this journey takes you ages because you're in the slow lane, whereas this journey over here is really fast because you're now in the fast lane. So once again, we're not in Euclidean geometry, we're in something different. The amazing fact is that the two things I've shown you, gluing together heptagons to make something really wiggly where things around the outside, there's more journey time around the outside than you might expect, and this model where you've got a fast lane over on the right so that distances on the right aren't as big as they seem. Mathematically they give you exactly the same space, which is hyperbolic space. So we really do have two routes into the same space at the end. Hi Aya, no need to apologise. There is a recording you can watch back anytime, and that goes for the other episodes we've had this season on Oxford Online Maths Club, and indeed the previous 6 seasons of Maths Club Fun. You can watch them all back at any time. Something fun that goes on in hyperbolic space, sorry, just to show you why this came about in the first place, is that if you've got two lines, they might cross in a point, or they might not, which, you know, you've heard of parallel lines, so that's no surprise. The fun thing is that, well, in Euclidean space, maybe you've got one fixed line, there's one with blue points, and you pick a third point. In Euclidean space, there's only one way to draw a parallel line through that third point, but in hyperbolic space, there's loads of ways to draw a line through that third point that doesn't intersect the first line. There's loads of options for your parallel line. It's sort of not a unique parallel line. All of these go through the third point but don't cross that blue line at all. So we've got some weird geometry here. A space where the fastest route from A to B is along a semicircle, which already looks a bit weird. And then the fact that you can have these kind of lines that feel like parallel lines, they don't cross. You get a choice about which one you're looking at. Okay. Hi everyone. I did get to a rule. Neutrino, I did it. I remembered at the end that I promised a rule. This was one of Euclid's postulates. It's notable for being proposed to be true about geometry in general, and then this is an example which does almost all of the geometry that you learn in school, except for the thing about parallel lines. The thing where you construct a parallel line through a given point not on the line works in Euclidean geometry, doesn't work in my fast lane traffic problem or on other models of the hyperbolic space. Okay, right. I think I need to put together loads of further reading notes, don't I, for about 3 different weeks. So that's my break. That's my break sorted. We're going to take 2 weeks off for Easter, so I hope you have a good holiday break. And we will be back on, I believe, the 18th of April. Yeah, let's do that. That's a good suggestion, Ben. Thank you very much. Let's do a quick plug for the concept of watching back other episodes. So here's the Math Club website, link on the screen and in the YouTube description if you want to catch up with previous things. We've been talking about roots to hyperbolic space. Quick rewind through previous episodes last week. We had Predators and Prey. So Leo was on the stream to talk about models of population dynamics. It's funny if you like mathematical biology. Had lots of things going on with Eve telling us about counting. I liked that one as well. The music maths episode was really good fun. If you didn't catch it, Maria on, who's a music student, telling us about music, and it involved both of these fractions. Matt Parker was on the show this term. So if you'd like to see Matt Parker talking about leap years, that happened on the 29th of February. Sophie McLean was on to talk about colouring problems. We had chessboards and things like that. Tarek told us about graph theory, projective geometry with Miles. If you liked this one and talk about weird geometry and how things might not be what they seem to your Euclidean eyes, then projective geometry, the way that railway tracks disappear onto the horizon, that was really good. We had Coralie on talking about maths and law, and which was a really interesting look at statistics. We had a couple of number theory episodes. We talked about SM primes, Fermat numbers. I tried to talk about wave theory right at the start of the year. And there was the Hydra episode where we tried to defeat the Hydra and discover very large numbers along the way. I think some of my favourite episodes this term have been the ones with guests on, which is actually almost all of them. I think I'm going to particularly shout out the music and maths episode for people who like that sort of thing. And it feels like picking favourites. I actually think Fake Primes was pretty good fun. Was that the one where we proved Fermat's Little theorem? Yeah, I think it was in the first episode, episode 0. And we've also got previous episodes if you want to scroll back even further to episodes from 2023 or 2022 or even 2021 when we did seasons 1 and 2. There's a lot of stuff on here, including previous guests who you've met before and other guests you maybe haven't seen on the stream unless you've been through all of our back archives. And yeah, I think I'm going to shout out Chaotic Viruses with Francesca out of the back episodes, especially if you like their kind of population dynamics. Good. Okay, thank you for the reminder that as well as plugging other people's summer schools, I should also plug the stream that you're currently watching. Good. Tell a friend. We'll be back in 3 weeks' time for more Maths Club fun. Until then, have a lovely evening. Have a good Easter, and we'll see you in... No, I've set myself up for failure here. We'll see you in several hundred hours. I've really set myself up for failing. I want to do it now. Don't look at that. Wait, hang on. So it's like 3 weeks. But take off 1, because I've been talking, and daylight savings. So daylight savings times happen in the UK where the clocks spring forwards, which means it's kind of stealing another hour. So that's happening in between now and then. There aren't any leap years or weird extra Thursdays or anything. Yeah, okay. I'm going to do it. I'm going to claim that's the right answer. We'll see you in 502 hours for another episode of the Oxford Online Maths Club. Take care. See you. Gosh, I hope that's correct.